Alright, so today in this lecture we are discussing the body water content. First, what is the body water content? Total body water is going to be determined according to the number of cells. All the cells will have cytoplasm on the inside, with one major exception for this general rule is going to be the fat cells. So fat cells will have mainly triglycerides on the inside of the cells, which will limit the availability of the cytoplasm. So the more fat content in the body, the lower the total body water. So who's going to have the least amounts of body fat? First is going to be infants. Infants will have around 73% of their total body weight in the form of water. Who do you think will have more water, males or females? Yes, females would have less water. Why would I have less water in females, do you think? Yes, I have more fat and less muscles. So males will have higher body water content, which goes up to 60%, or is going to be around 60%. Compared to females, it's going to only be around 50% of their total body weight. So again, why males will have more water compared to females? Because simply males will have more muscles and less fat. What do you think is going to happen if I'm dealing with old age person? So as a person gets older, he's going to accumulate more fat, and the higher the body fat content means less total body water. So in older age, I have a lower body water content that goes down to around 45% of the total body weight. Moving on to the distribution of this body water. Body water is going to be divided into two major components. First component is located inside the cells. This is called my intracellular fluid content, and the other part is going to be outside of my cells, and this is going to be my extracellular fluid content. Extracellular fluid is going to be divided into two major compartments. I have the amount of fluid located inside my blood vessels. This is going to be considered my plasma. And the amount of fluid that will be surrounding my cells, this is going to be my interstitial fluid. Intercellular fluid is representing 2/3 of the total body fluid content, compared to my extracellular fluid is going to represent the remaining third. I have extracellular fluid which won't count as part of the plasma or as part of the interstitial fluid, as it's going to be like the fluids inside your eye. If you remember, in the eye I have the fluid occupying the posterior segment of the eye. This is my vitreous humor. And I have the fluid compartment that occupies the anterior segment of the eye, and this is going to be my aqueous humor. Also, I have fluid located in my gastrointestinal tract. This is not going to be considered part of the plasma, it's not going to be considered part of the interstitial fluid, and it's not part of my intracellular fluid, still part of my extracellular fluid. So the gastric juice, the intestinal mucus secretions, also is going to be part of the extracellular fluid, but not going to be participating as part of the plasma or part of the interstitial fluid. Also the fluid in the serous membranes, like the membrane around the lungs, if you remember, called the pleura, the membrane around my heart, my pericardium, and the membrane around my abdominal organs. This is what we've called the peritoneum. So all those serous membranes will have fluid, and this fluid is not participating as part of the plasma or my interstitial fluid, but it's still going to be part of my extracellular fluid. Also, the fluid inside my synovial joints, if you remember, this was my synovial fluid between two articulating bones. In this space between the bones, I did have fluid. This is called my synovial fluid. Still going to be part of my extracellular, but not part of my plasma or interstitial fluid. What's going to be the composition here of the body fluids? Body fluid is going to be mainly formed of water that represents more than 90%. Why water is so important to us? Because simply it's a universal solvent. In order for any chemical reaction to take place, it needs a medium. So in order, for example, for the sodium to interact with chlorine, I need to have a medium through which the chemical reaction will take place, and the medium here is going to be my water, which will act as a universal solvent. Also, I have the solutes that will share in the formation of my body fluids. This can be in the form of electrolytes or non-electrolytes. Electrolytes can be like the inorganic salts, like the acids, bases, and some of the proteins. Non-electrolytes gonna be like the glucose, lipids, creatinine, and urea. Extracellular fluid will be different in terms of solute content if I compare it to the intracellular fluid. So for example, the major cation inside my cells is going to be my sodium, compared to the major cation outside of the cells in the extracellular fluid compartment. This is going to be my, I'm sorry, here. So on the intracellular fluid compartment, the major cation is going to be my potassium, and on the extracellular fluid compartment, my major cation is going to be my sodium. Same will be applied for all of the different solutes. I have different concentration of the different solutes on here, and between the intracellular fluid and the extracellular fluid compartments. So you see here, much more sodium going to be located in the extracellular fluid in both my plasma and my interstitial fluid, compared to much more potassium is going to be located in the intracellular fluid compartment. Same would be applied for something like the chlorine. Chlorine is going to be much more prominent in the extracellular fluid compared to the proteins. For example, I have high protein content inside my cells because simply proteins are going to be performing many of the major metabolic activities of the cells, and I will have lots of proteins as well in my plasma because of the presence of the plasma proteins, which are going to be responsible for many of the functions of the blood. Compared to the compared to the interstitial fluid compartment, I don't have much protein because I don't carry any major function in this fluid compartment. Fluid is going to be moving according to two major pressures. First pressure is going to be my osmotic pressure, and the second pressure is going to be my hydrostatic pressure. So let's stop here for a second and look back at what is meant by hydrostatic pressure and osmotic pressure. So hydrostatic pressure is simply speaking the pressure of the fluid in any compartment. So if you have much more fluid on one side, fluid tends to move from its high pressure, where you have much more fluid, to the side with lower pressure, or in other words, much less fluid. So the fluid volume here plays a major role in the determination of the hydrostatic pressure. Also, the pressure by which the fluid gonna be moving. So for example, your vessels are gonna be, or your arteries gonna have a much higher hydrostatic pressure because they receive blood due to the contraction of the ventricles of the heart. So I am applying much more pressure on here. I'm squeezing the blood to travel into my arteries. So this will allow the fluid to travel at a much higher velocity, creating a much higher hydrostatic pressure compared to my osmotic pressure. What is osmotic pressure and what determines the osmotic pressure? If you remember, in any solution, I have a ratio, which is a concentration, the concentration of the solutes. And what I mean by the concentration of the solute is the amount of solute diluted in an amount of solvent. So for example, if I have 1 mole of solute X, this is an amount of the solute, but when I dilute this mole into 1 liter, so now it's a concentration. I have the concentration of the solute X is going to be 1 mole per liter. If you remember, any substance is going to be trying to move from its higher concentration gradient to its lower concentration gradient. But what if the membrane I'm trying to travel through is impermeable for this solute to travel? So here I'm not allowing the solute to travel down its concentration gradient. So let's say in this vessel on here I have 3 moles per liter. On the other side of the membrane I have only 1 mole per liter. So here on this side of the membrane I have a much higher solute concentration compared to the other side. So what do you think gonna happen? The solute itself is not able to travel down the concentration gradient by diffusion, but if I'm looking at the ratio now, I have here 1 mole per liter. In other words, this is gonna be 3 moles per how many liters? What do you think? Yeah, per 3 liters. So it's the same. 3 moles per 3 liters of water is gonna be the same as 1 mole per liter. Same concentration. So I didn't change the concentration on here. So if you look at the concentration of the water now, amount of water on this side of the membrane is much higher compared to the inside of the vessel. So having a lower solute concentration means I have much higher water concentration on this side, and having high solute concentration on the inside of the vessel means I have lower concentration of water. So having low solute means I have high water content, and having much higher solute content means I have lower water content. So the membrane is impermeable for the solute to travel, but it's not impermeable for the water to travel. So the water now will start to travel from its high concentration gradient to its lower concentration gradient, or in other words, the water is going to be traveling from low solute concentration, which we mentioned that it has a high water, to the side with high solute concentrations that we just mentioned that it's going to have lower water concentration. So water here travels for free. It's a passive process. Water tends to travel down its pressure gradient, which is opposite to the pressure gradient of the solute. This water transport is taking place by a special transport that we call osmosis. So simply speaking, what's osmosis? Osmosis is the transport of the water from low solute concentration to the side with high solute concentration if I have an impermeable membrane for the solute. Putting this into account, so what we've mentioned so far is that water travels from low solute to high solute. This is what we call osmosis. So if I did have one fluid compartment which has higher solute content compared to another compartment which has lower solute content, so this means water will be moving like this from the low solute side to the high solute side by a movement here that we call again osmosis, a membrane transport that we call osmosis. So who did apply a suction force for the water is going to be the side with higher solute. Solute here is going to be pulling the water to its side. So what we're going to see throughout the kidney and the fluids of the body, that whenever I have high solutes, water is going to be following the solute, whatever the solute is. Each solute applies a specific osmotic pressure, and according to the characteristics of the different solutes, you're going to be putting more or less water, as we're going to see. Water here moves freely by osmosis, and the osmolality of all the body needs to be equal. Why do you think it needs to be equal? If I told you, for example, this is one of your cells, and this is your extracellular fluid, and this is one of your vessels. If I told you that I have much more solutes in my cells compared to my plasma, what's going to happen? Water travels from low solute to high solute. So what's going to happen to those cells? They will be swelling. Would you like your cells to swell? I don't. So here, what I see, it's impossible to have higher solutes in my cells. What if I did have high solute content in my extracellular fluid compared to my cells? My cells would have lower solute content. So what's going to happen to those cells? Those cells will be losing the water to the outside. Water moves by osmosis from low solute concentration to high solute concentration, and as a result, those cells will shrink. So I don't want my cells to shrink. I don't want my cells to swell. So I need to have equal osmotic force in the different fluid compartments. So if I'm looking here, in order for me to not have neither a net gain or a net loss of the fluid between the different compartments, all the different compartments will need to have equal osmotic pressure, or in other words, equal total solute concentration.